The periodic table is a tabular arrangement of chemical elements organized by their atomic number, electronic configuration, and recurring chemical properties. It's a systemic way to display all known chemical elements, showcasing trends in their physical and chemical behavior. Hey everyone, welcome to Sketching Science. Today we are diving into one of the most iconic tools in all of chemistry, the periodic table of elements. The periodic table was the brainchild of Mendeleev, a Russian chemist. The table layout we use today evolved from a system he developed in 1869, but that was inspired by many earlier attempts to organize the elements. The first one is the alchemy. Alchemists, the wizard-like forebear of modern chemists, organized substances according to their magical properties. They gave them symbols and genders and attributed to them links to the planets. This table was put together by Basil Valentine in the 15th century. In 1718, Etienne Francois Geoffroy listed substances using their alchemical symbol according to how they combine or interacted. These are called the affinities. Antoine Lavoisier drew up a list of substances simple in 1789. This was one of the first attempts at a table of elements, although it included light, heat, and several compounds. Next, John Dalton was the first chemist to show that elements worked as atoms. In 1808, he produced this table which ordered elements by relative weights. In 1817, Dobereiner developed the law of triads, in which he found several sets of three elements that each seemed to share same properties. It was first published in 1829. In 1864, John Newlands saw that even though every element had a unique relative weight, no two weighed the same. Their chemical properties followed a pattern, repeating after every 8 elements. He called the group octaves and even tried to present the system using a musical score. And finally, in 1869, Mendeleev turned the repeating or periodic patterns of elements based on their atomic mass seen in the valence of elements into the periodic table we know today. However, the first attempt shown here uses columns for the periods, not rows like we use today. The modern periodic table shows the element in order of atomic number, the number of protons their atoms have. The elements are also arranged in rows known as periods so that elements with similar chemistry are lined up into columns or groups. In this version, elements with similar properties are shown by the color categories. The first element of modern periodic table is hydrogen. Then the alkali metals come, a group of reactive metals occupying the far left column of the periodic table. They are all soft, but they are solid metals at room temperature and never appear pure in nature. Then the alkaline earth metals, which are silver, white metals at room temperature. The name is a term that refers to many naturally occurring oxide of these elements found in or derived from rocks. For example, lime is the alkaline oxide of calcium. The transition metals make up the central block of the periodic table. They are harder than the alkali metals, less reactive, and are generally good conductors of both heat and electric current. The lanthanide element occupy a horizontal strip normally appended at the foot of the periodic table. Named after lanthanum, the first element in the series, They are generally found in large amount in uncommon minerals such as monazite. Then the actinides come, which make up the second horizontal strip at the foot of the table, named after their first element, actinium. They are all highly radioactive and include the main sources of nuclear fuel. Then the post-transition metals, also known as the poor metals. This triangular region contains unreactive metals that have weak metallic properties. They mostly have low melting and boiling points. The metalloid elements form a divided between the metals and non-metals in the periodic table. Their electrical properties are intermediate between these other two categories, leading to their use in semiconductor electronics. Then the other non-metals come, a loose collection of elements that do not fall into the halogens and noble gases and are therefore shown here as a separate group. However, they display a wide range of chemical and physical properties. Most nonmetals have the ability to gain electrons easily. They generally have lower melting points, boiling points and densities than the metal elements. Then the halogen comes. The halogen, also known as group 17, are the only group to contain all three principal states of matter at room temperature. Like fluorine and chlorine are in the gaseous form, bromine is in the liquid form, and iodine and astatine is in the solid form. And all of these are non-metals. Lastly, in the group 18, there are noble gases. These are non-metals. They are all gaseous at room temperature and share the properties of being colorless, odorless and unreactive, including neon, argon and xenon. They have application in lighting and welding. Finally, there are some elements which are having unknown chemical properties. Elements larger than uranium are generally made in the laboratory and very often only in minute quantities. The chemical properties of several of the latest and largest artificial elements remain something of a mystery. That's all for this video. I hope you enjoy. Thanks for watching.